Okay, guys, I will not be with you today, but I do have some things that I want you guys to do, and we'll try to walk through them on these videos. The first thing that I want to make sure is that you guys have your graphs on, cut out your graphs on page 117 and 119. So if you guys look at them, this is like 117. These are the graphs on 117 that I want you guys to have cut out. And these are the graphs on page 119 that I'm looking for you guys to cut out. So make sure you guys have those cut out for me. And then also, if you guys can make sure that you guys have taped the arithmetic sequences that we were working on yesterday, which were B, H, E, N, and K. Make sure you guys have those taped to page 121 all the way to 125. Okay. And then do the same thing with the geometric sequences. Make sure you guys have A, C, F, J, M, P taped to pages 126 to 130. So that's the first step here. I would also just make sure that you guys have tape with you, have tape and scissors. That'll help you guys today, and also your book. All right, so I would encourage you guys to pause this until you guys have that done, and then I'll continue on. So just remember, guys, this is what we're trying to get ready for today. Make sure you guys have your textbook ready, have some scissors and tape, and that you guys have taped A, C, F, J, M, and P to page 126 to 130, and then you guys have taped P, H, E, N, K to page 121 through 125, and you guys have cut out all of the graphs on 117 to 119. So you guys will have like a whole bunch of the graphs. Okay, so if you guys could try to make sure you have that. I'm going to continue on, guys, just to kind of walk through what you guys are working on right now. Okay, just remember, guys, we were talking about arithmetic sequences. All right, and we were just talking about how arithmetic sequences, the difference between any two consecutive terms is constant, and that constant difference is called the common difference. And we talked about the idea on page 105 that the way we find that common difference is like we take the second term minus the first, the third term minus the second, fourth term minus the third, and that should be exactly the same. So like in this example, we said, okay, second term was 9, and we subtracted 11, we got a difference of -2. The third term was 7, so we did 7 minus 9 to get -2. And then we did 5 minus 7 to get a difference of -2. So our difference is -2. Okay. On page 106, we looked at another example in which we had a difference of 4. And what we were able to determine is the difference between this sequence and the one that we did previously is that what we are adding is different. Before we added -2, now we're adding +4. That still makes it an arithmetic sequence because we are adding the same thing every time to get the next term of the sequence. So that's what makes an arithmetic sequence an arithmetic sequence. And we were able to come up with, on page 106, 11, 15, 19, 23, and 27 to be the sequence. After that, guys, you guys then taped the sequences that were arithmetic on pages 121 to 125 in your book. Okay, so there's arithmetic. Okay, so if I look at geometric, a geometric sequence is when it has like a common ratio, like a fraction or a value, integer, in which I multiply and it gets me the next term of the sequence. So it has a common ratio. That's what a geometric sequence is, and we multiply each term by a constant to determine the next. The way we figure out that common ratio is we took the second term divided by the first term, or we took the third term, which was 4, over the second term, which was 2, and then we took 8 divided by 4, the fourth term over the third. In this example, that common ratio was the same. It was 2. In question 3, we were then looking at, okay, well, what happens if I'm starting off with the same number 1, and my common ratio is 3? Well, the only difference, the main difference, is what I'm multiplying by has changed. Before, we multiplied by 2 in this example. Okay, in this example, we're multiplying by 3 every time. So is it a geometric sequence still? Yeah, it's a geometric sequence still, because we're multiplying by the same term every time. We're multiplying by 3. So if we go 1 to 3. 3 times 3 gets me 9. 9 times 3 gets me 27. 27 times 3 gets me 81, which makes that a geometric sequence. If you guys feel adventurous, you guys could try number 4, and I can talk about that tomorrow. In this case, we're starting off with the same first term of the sequence. We're starting off with 1. But in this case, my common ratio is 1/3. And you guys were asked to figure out what are my next 6 terms going to be. Yeah. So if we start off with 1, 2, 3, 4, 5, 6. So if this is a common ratio of 1/3 and I started off with 1, what would be the next 3 terms of my sequence? So you guys could try that. I encourage you guys to try that, and we'll definitely talk about that tomorrow. Okay. Now, at the bottom, it says that we talked about we having a sequence that started off with 1, and it had a common ratio of -2. So we talked about how that only difference is that it's going to be the same values as what it was in the worked out example, except that they're going to be alternating positive and negative. See, it went 1, 2, 4, 8. Well, in this sequence, 1 times -2 gets me -2. -2 times -2 gets me 4. 4 times -2 gets me -8. -8 times -2 gets me +16. So that's the pattern that works out for that. Okay. So, what we are looking at is we're asked to consider the sequence shown in which we have 270, 90, 30, and 10. Devin says that he can determine each term of the sequence by multiplying each term by 1/3, so the common ratio is 1/3. Chase says that he can determine each term of this sequence by dividing each term by 3. So, the common ratio is 3. Who is correct? And explain your reasoning. So, I want you guys to try to think about this one. What is going on? Like, what is Devin saying? Like, what is Devin saying about the common ratio? Okay. And what is Chase saying about the common ratio? What are they saying? Okay. Write down what those values are. Okay. And after you guys are done writing those values, try to figure out, based off what Devin says or what Chase says, see what their sequence is and see which one aligns with this. And I want to talk to you guys more about this tomorrow, just to see what you guys determine. Okay? All right. So, you guys have done this one, 7. So you guys said consider the sequences you cut out. So we taped all of the geometric sequences to the pages that we had to. Okay, so we've done this. Now let's look at question 8. We have some sequences that we have not used. Okay, so consider the sequences that are neither arithmetic or geometric. So like if I look at D, that is not arithmetic, it is not geometric. G is not arithmetic, it's not geometric. L, I, and O. All of these are not arithmetic, they are not geometric. There's a pattern. These all have patterns. But remember, in order for it to be arithmetic or geometric, I have to be adding or subtracting by the same number every time to get to the next term of the sequence. Okay? So like if I look at D, I'm adding a number that's increasing every time by the same value, but I'm not adding like 7 every time to get to the next term of the sequence. We'll talk more about this in the future, but like the second difference is the same, which creates a new pattern. But in this case, all we care about is what that first difference is, and it's not the same. G, they're alternating, but there is no like number that I'm multiplying or number that I'm adding that gets me that next term. Looking at this one, L is very similar to D. That first difference, I mean, there's a pattern to what I'm adding, but it's not consistent in what I'm adding to get to the next term of the sequence. And then I is the same, in which I am adding a number that's increasing, but what I am adding is not the same thing every time. Like, if I were to be adding 3 every time, if I were to add 3 to 2, I would have gotten 5, but I got 7, so it doesn't work out. And then for O, I'm taking the square root of a number that's decreasing, and that's not an arithmetic or geometric pattern. So with these 5 cards, we don't need those. You guys could put these to the side. If you guys even wanted to throw them away, you guys are okay with that. So you guys can discard O, I, G, D, and L. You guys can discard those cards. Okay? All right, so what I'm going to ask you guys to do, one of the things that I'm going to ask you guys to do, I'm going to ask you guys to look at page 110. Okay? And I want you guys to try to answer 9, 10, 11, and 12 for me on page 110. That's one of those assignments I'm going to ask you guys to do. Okay? On page 110, I'm going to ask you to do 9, 10, 11, and 12. With, on page 108, number 4. Okay? And page 109, number 6. Okay? I want you guys to try those problems, and they'll be posted on Classroom, and I'll even leave a note for you guys about what you're supposed to do. So written down for you guys, I'm asking you guys on page 108 to try question 4. On page 109, I'm asking you guys to try question 6. On page 110, try questions 9, 10, 11, and 12. That should take you guys a couple minutes, and when you guys are done, I'm going to ask you guys to watch this next video that deals with graphs of sequences.